All right, so now that we have the descriptions of the probability distributions and shapes of all the atomic orbitals, we can start understanding the electron configurations of the neutral elements, right? By populating the electrons and going by this Aufbau principle, this building up of electrons in these atomic orbitals to give the electron configurations of the neutral elements. And so, we start with hydrogen, first element, one proton. So a neutral hydrogen has one electron. We're going to put that in the lowest energy atomic orbital that there is, the 1s orbital. That will be the ground state of hydrogen is having a 1s1 electron configuration. We could call that electron as having spin up ms equals plus 1/2, or it's arbitrary. You could call this minus 1/2 as well. Our second electron is going to go in the 1s orbital as well and have the opposite spin. So now we have helium with an electron configuration of 1s2 and spin up and spin down. And then we get to lithium, right? And we know that we're now going to be at principal quantum number of n equals 2 for where that third electron goes, right? Because we've populated, there aren't any 1p orbitals to go into, and we've filled up the 1s orbital. We can't put another electron in there because whether or not it's 1s or whether or not it's spin up or spin down, it'll have the same quantum numbers, and due to the Pauli exclusion principle, we can't do that. All electrons must have different quantum numbers, a unique set of quantum numbers. So where does that third electron go? It's going to go in a 2-something orbital, right? Our options are 2s or 2p. And, a valid question at this point is, how do we know if the 2s or 2p is lower in energy? Now, in sort of general chemistry, you're just taught, hey, look at the periodic table. Maybe that's how you're taught. Look at the periodic table. Look, there's 2 elements here. So the third electron is going to go there. Fourth electron is going to go there. This is 2 wide, so that's the s. But that doesn't really get to why the 2s is lower in energy. Why didn't you go to the 2p before the 2s? Okay, and so this has to deal with the specifics of the electron probability distribution, and so and specifically something called electron shielding. So now we're into these multi-electron systems, and so not only do we have to think about electrons being attracted to the nucleus, right? But we also have to think about electrons repelling each other. And so, if you think about an electron close to the nucleus, yeah, it's mostly feeling this electron, but it's the nuclear charge, but it's also feeling these electron-electron repulsions, right? And you can imagine that if your electron on one of the outermost orbitals, like let's say you're in the n equals 2 versus the n equals 1, well, you're going to feel more repulsion. And you're gonna feel repulsion from the inner 1s electrons, and as a result, your attraction to the nuclear charge, the positive nuclear charge, isn't going to be as great. And so we call this effect electron shielding. In other words, these 2 1s electrons, the 2 electrons that are in the 1s orbital, shield some of the nuclear charge, the feeling of the nuclear charge, the attraction of the nuclear charge, from this 2s or 2p electron, whatever it may be, okay? And so there's a way to quantify these effects, and that's by looking at what the actual nuclear charge is, okay? This is the definition of an element, the number of protons. So if we're talking about lithium, this is going to be 3, z equals going to be equals to 3 here. And comparing that to what's called, given the abbreviation ZF, the effective nuclear charge. And this is the nuclear charge a given electron feels when taking into account that that electron-electron repulsion, when taking into account electron shielding. So in other words, the effective nuclear charge that this electron feels in the outermost shell is going to be much less than the effective nuclear charge that the n equal 1 electrons feel, because again, the n equal 2 electron is more shielded from the nucleus by the n equals 1. And the n equals 1 electrons are closer to the nucleus, so they have a higher effective nuclear charge. And so effective nuclear charge, ZF, will always be less than the actual nuclear charge. The textbook goes over some empirical rules called Slater rules of how you can actually estimate what the effective nuclear charge is for these electrons, no matter where they are. But we're not really going to emphasize that, or I'm not going to test you on that in this course. And so again, now we can answer this question: why is the 2s lower in energy than the 2p? Okay. If we look at the radial distribution diagram, remember that the 2s had this kind of like core-like behavior, right? In other words, there was a little bit of electron density at close to the location of the 1s, very close to the nucleus. And that same sort of distribution doesn't occur, okay? There's no feature like that very close to the nucleus for the 2p radial distribution function. So what we say is, when the electron's right here, very close to the nucleus, it's going to feel a very strong effective nuclear charge. When it feels that, that's negative and positive coming together. That's a stabilizing force. That's a stabilizing energy, right? So this is why, it's because of this little feature here, this is why the 2s is lower in energy than 2p, okay? And what we say is that the 2s has more penetration. It can penetrate. The electron density can penetrate closer into the nucleus, feel that good, quote unquote, right, negative to positive attraction that stabilizes the system, whereas the 2p can't, it doesn't have that same level of penetration towards the core, and so it's going to be higher in energy. And so in general, s orbitals have more penetration than p orbitals in this way. Okay, and this is why s orbitals with the same principal quantum number are always more stable than the p orbital. The corresponding p orbital. So the 3s is more stable than the 3p. The 4s is more stable than 4p. The 5s is more stable than the 5p, etc. So you can look at some of these Z effective numbers. For boron, for example, boron has 5 protons, so Z equals 5. That's just the number of protons, the charge of the nucleus. But you can look at it for the different electrons in boron. Boron's going to have 2 electrons in the 1s, 2 electrons in the 2s, and then the 5th electron is going to go in the 2p. And for the 1s electrons, it's pretty close to 5. It's 4.68 is the ZF. Why is it not exactly 5? Well, the 2 electrons in the 1s are shielding one another a little bit. They can't too much because they're in the same vicinity most of the time, right? But when you get to the 2s, look at how much dramatically lower it goes. It's almost cut by half versus 5, right? So each of the 2s electrons is only feeling effectively about half of that +5 charge at the nucleus. And that's because they're being shielded not only by each other, but more importantly, by the 2 1s electrons. And then you can see the 2p, it's slightly lower than the 2s. Not as dramatic, okay, because it's the same principal quantum number, but it is a lower effective nuclear charge. That lower effective nuclear charge is another way of saying, or is reflective of the fact that the 2p is less stable. It's higher in energy than the 2s. And so that's what this is saying here. 2s experiences less shielding, more penetration, a greater Z effective, and thus is more stable than 2p. All kind of ways of saying similar things.